uniformly loaded, concentrated. So, they will keep on expanding like that. In our case, it is not like that. If it is beams, beam bending, that is all. 2 words will cover everything. It may be simple beam, it can be redundant beam, it will be having this type of beam or that type of beam. So, then what happens is the teacher and the student, they will try to judge each other. If the teacher sees that the students can grasp it, they have the capacity to grasp at a faster rate, he will go in an accelerated manner and he will try to deliver as much as possible. The limit is whatever you can grasp. If he finds that students are not in a position to grasp, then they will say, it's okay, let me go slow. And again, the examination the same way. So, no set pattern. In fact, over the years now, a pattern has become set. But there is not supposed to be set pattern, no supposed to be distribution, known distribution, something of that. Like our so, that's what happens actually. Anyway, we start with the analysis of bulkhead. Now, before we go to the topic of bulkhead for the analysis, we should try to understand that why bulkheads are required. And once we know why bulkheads are required, then only we will try to gauge what type of analysis we require. So, let us say use of bulkhead. This can be listed like this. Number 1, that when we say bulkhead, it can be transverse bulkhead or it can be longitudinal bulkhead. Okay. So, we try to differentiate between the two and we say that transverse bulkhead. The first and the foremost is that these transverse bulkheads are required to subdivide the ship into number of compartments. So, subdivision into number of compartments. Then we try to add an adjective to it. What type of compartment? And then we say that we require the safety aspect. And first thing, because the ship is floating in water, so the first thing comes into our head that it should be watertight compartments. So, below let us say watertight. That means when we are having watertight compartments and in case of any damage, a particular hold gets flooded, the ship should still float. Okay. So, that means the main purpose is to provide reserve of buoyancy. In case of flooding. Depending on the type of ship, whether you have one compartment standard or more compartment of standards, more compartment means 2 adjacent compartments or so, that will decide, and accordingly we try to subdivide it. So, this is one part of it. We can further extend that it is not only watertight, you may say it should be gas tight, it should be fire tight, and so on and so forth. Many a times we say weather tight also. There is some difference between watertight and weather tight. I suppose you know all the differences. So the first aspect is from the safety point of view. Next comes the strength aspect of it. Now, the ship as a whole, if you just consider on the wetted part of the shell, then it is a envelope which keep the sea out and the inner space intact from the sea. All along this shell, you will find that the water is exerting pressure in the normal direction, and the vertical component of it is being equated by the weight, but the horizontal direction is supposed to get cancelled provided the force comes in action equal and opposite. Now, if there is no member there, then how the forces will be transferred from the two sides, and therefore, you have these bulkheads which provides the transverse strength. If you do not have this, then the two sides will collapse. Okay. So, the major part is transverse strength. So, the water pressure which is being acted upon on the sides is getting transmitted through this, and the bulkhead comes from the two sides in sustaining the in plane forces. So, that is the type of load which is being transferred to this transverse bulkhead. Okay. Number 2, the ship rolls in the quarter sea or beam sea. In that case, some sort of a twisting moment is generated, and because the whole hull girder is a hollow box, these intermediate walls try to act as diaphragms and provide torsional rigidity. That means, apart from the direct in plane stresses being transmitted to the bulkhead, there is an in plane stress also. This in plane stress is basically the shear stress too, because of the torsion some shear stress will be generated. So, this is also subjected to apart from the in plane direct stress, some sort of in plane shear stress. And the very first, that subdivision of the ship and providing reserve buoyancy implies that when the compartment is flooded, that means there is a water inside, and water will try to exert pressure from inside to all the 5 parts, namely the 2 sides, the 2 bulkheads and the bottom. So, this implies that the bulkhead is also subjected to transverse loading, or bulkhead is subjected to load in plane normal to its plane, that means exerting some sort of a flexural deformation or bending, right. So, now once we know what is the use of the bulkhead, the forces are automatically coming into the picture. What are the forces which are coming into picture? So, then we can say the forces acting on a bulkhead. We can name them in plane stresses or in plane forces, B in plane shear forces, and D is the bending forces. Of force in out of plane direction. Okay. So, after defining this, then let us try to draw the bulkhead. It's okay. Let us put the water line here. So, this is the hydrostatic loading coming from here. This is the load coming from the bottom pressure. Okay. Then you may have some sort of a shear loading here. Right. Then let us take a section somewhere here. Draw the plate. This is the bulkhead plating, and then the hydrostatic loading in flooding condition will go right up to the top.
There is complete flooding.
When we say flooding condition, then we are saying that it is still floating, but wherever is the, whether it is up to the deck or up to some predefined line or whatever it is. Okay. So, this is loaded like this, right. Now, this is the load which we have seen, but if you see the construction, then usually what we will find that somewhere here you will have a double bottom here, a usual construction technique. Within the double bottom you will have certain girders here, and the bulkhead, this is the inner bottom. Maybe that you can have some sort of a intermediate deck, okay. We can say some lower deck, and then there are stiffeners provided to this plate here. I am simply drawing with the dotted lines at some constant intervals. Okay. So, this stiffness I can draw it here. And maybe they are connected with some sort of a bracket here. Okay. So, you have two sets of forces, one is in plane force, another is out of plane force. So, these are in plane forces and this is the out of plane force. They are all acting simultaneously. Now, if we try to analyze them on by any analytical method, then this shape will come into our way. But for the analysis sake, we can always consider it to be a perfectly rectangular plate and we can try to analyze the plate. Now, the method of analysis of this can be listed like this. You can have one method it is a two-dimensional structure. You have a two-dimensional plate in one plane and then on that plane you are having some stiffness. So, basically it occupies some volume and the volume means 3 dimensions are active in Cartesian system, and truly speaking one should try to do a 3D analysis. But then the basic plate is in 2-dimensional and the beams can be considered that it is embedded to the plate. We can reduce the 3 dimensions to 2 and we can consider it to be a 2D problem. Usually the detailed analysis is done on the basis of 2D method, and there are plate and stiffness and therefore two methods can be adopted here. One is known as the orthotropic plate analysis and the second one is plate stiffener combination. And obviously we have started with 3D, we have come to 2D, and if we take advantage of uniform spacing of the stiffeners, all over S, and we also assume that all stiffener sections are identical, then we need take one strip out of here and try to analyze it as a beam. Okay? Only one part of it we take, this much of plate with one stiffener, and try to analyze it as a beam, and then we come back to a one-dimensional analysis. That means you simply consider it to be a beam. Obviously, if you go in the reverse order, this is the simplest of the lot, then this becomes slightly tougher, and this is the toughest of the lot. Of course, when we say that the bulkhead lies in a plane, and if you take the plate and stiffener combination for the analysis, should give me a reasonably good result. If I try to take it as an orthotropic plate, then it should give me slightly inferior result, and on the basis of one dimensional analysis I should get a cruder result. Okay. And it is quite obvious that if one can perform a 3D analysis, should give the best result, and if the problem can be done by any analytical method in a complete manner, then that should give you the exact result. But the shape, the loading and the practical nature of the bulkhead will come in the way for a perfect analytical method solution, and therefore some sort of an approximate method has to be applied for the analysis, and then it depends on the analyst that at what stage he is performing the experiment analysis, depending on which what is the expectation of accuracy from the analysis. Okay. So, based on the accuracy level, we try to start the thing. So, let us see that we are broadly interested in how to design the thing. The greater analysis can take place later on. Then we go for the beam analysis. So, we consider plate beam or the plate stiffener combination to be a beam. When we consider this to be a beam, then let me draw the bulkhead once again. Say main deck, second deck or lower deck, tank top and bottom. The stiffener here, put brackets here. Okay. Let us assume that this height is h. It is flooded up to this, so I am interested only in this part. So, the loading is in this fashion. You may ask me that I have not shown any in-plane loading here. Okay. Two things. When we are considering the flooded condition of the bulkhead, then the stresses generated due to the transverse load is much larger than whatever is imposed due to the in-plane stresses. Okay. So, if we try to isolate in plane with the out of plane, we find that it will be better to just make an analysis on the basis of out of plane method, and then we can also superimpose the stresses calculated on the basis of in plane forces. But yes, when we try to do a detailed analysis, at that time attempt is made to take all the forces simultaneously to get the true nature of the stresses in that particular structural element. Right? Now, here my primary member is between the second deck and the tank top, because the span is more and the load is of this nature. So, we set up, we are considering it as a beam. So, from here I set up some coordinate system and I say that my x is measured this way to some level here, right. Now, if you take a cross section here for this particular strip, you will find that this is the plate width to which some stiffener is attached, usually a bulk plate, and at this level a constant pressure is acting here, which is of this intensity. Okay, I have just taken a cross section here and drawn here, right. Now, this spacing, as we have seen, is S, and if we say that the water density here, or whatever you call it, per unit area, then the pressure which is acting here, or the loading onto this beam, the intensity is W into S, and the pressure is basically the distance between from here to here. This is your rho. Rho is embedded here. Okay. Mass per unit volume into acceleration due to gravity is this. And so, actually what we are trying to do here, this is the pressure multiplied by the rho, and acceleration due to gravity is giving me the intensity of force at this, and this is the strip on which that intensity is acting. So, basically multiplying by that frame spacing gives me the intensity of loading at that particular position of the bulkhead plate and stiffener combination. Okay. So, now for this bending analysis, I can say the basic equation, which in 2-dimensional d4y by dx4 is written as Ws h plus x. That means the fourth derivative of the displacement with respect to the linear coordinate gives you the intensity of load, and from here the first integration will give you ax square, or x square by 2 and plus a constant of integration. So, let me put a here. Okay. I am trying to follow this notation, so that then the second integration will lead to, I think I will bring it here. So, anyway, does not make much difference. Next integration, which gives you the slope, and then finally the last integration will give you Okay. Now, A, B, C, D are the constants of integrations, and they have to be obtained or evaluated by applying the boundary conditions at these two ends here, right. So, before applying the boundary conditions, let us discuss something about this. Now, we have a stiffener here, we have a bulkhead plate here. This bulkhead is welded to the tank top. This bulkhead is again welded to the second deck here, which is a line contact. And then we have tried to connect the lower foot of this particular stiffener with the help of a bracket. This bracket can be a simple bracket, it can be a flanged bracket to the bottom plate here or the tank top, and here again to the top of the second deck or the underneath of the second deck by bracket. Now, they will try to provide some sort of a rigid connection, but one thing we should not forget, that this tank top is again made of thin plates, thin structure. The second deck is also a stiffened plate structure. So, basically the plate to plate contact is a thin plate made of more or less the same material, normally the same material, mild steel. It is possessing the same elasticity. So, when this pressure is acting on it, this will try to bend the structure here, and when it tries to bend it, because of this bracket we are trying to make the connection rigid, but this being of elastic material, the entire top structure will try to rotate like this. Okay. No buckling now. Buckling is not there. See, what is happening is, this is one plate, this is another plate, okay, and we say that we have put some bracket here. So, that bracket is a small thing here. So, what we are trying to do, we are trying to apply some load here, so that this will have a bending. Now, at this particular point, the connection is rigid, but this being made, the top is also made of elastic material, it is quite likely that this 90 degree will be maintained, but the whole thing will rotate like this. Under this action of force, the whole thing may rotate, and therefore, this part is coming into play to resist this rotation. This 90 degree remains 90 degree. So, putting it back on a piece of paper, because of this bracket connection, okay, I am in a position to maintain this 90 degree, okay, but the whole thing can rotate like this, because this is in a position to rotate. Okay. So, as far as this connection is concerned, the connection is rigid at that particular point, but as far as the structure is concerned, structure is having a freedom to rotate in a limited manner. Now, this is what is important here, that we will say that by providing the bracket it becomes rigid, but at the same time the structural configuration is such that it does not behave like a rigid connection. It is okay. Now, here we differ from the standard boundary conditions, that the slope is 0 or the moment is 0. As you can see that there is some slope, it is not 0, but as we can see that the joint remains 90 degree, both the conditions are being met here. A part of simple support condition, that it allows the rotation, at the same time the 90 degree remains 90 degree, which is a part of fixed end condition. It is a very difficult type of a joint. We have welded it, yes, and that is because the material property. When we talk in concrete beams, then such a heavy wall and this and that, we rarely find any visible deflection there. but here these types of deflections can be measured if you use a theodolite or some such thing. Okay. So, this was being realized earlier, and one said that it has got a limited rigidity, or you can say limited flexibility, and then we say some sort of a end fixity. The term used is end fixity. It is neither 0 nor 100. It is in between the two. But what is this quantity is a question mark. If we say end fixity is 0 means simple support condition, if end fixity is 100%, fixity is 100%, then it is a clamped condition, rigid condition. But as we are seeing, neither it is simple support nor it is rigid, it is something in between the two, but how much it is a question mark. Okay. But we realize that it is something between 0 and 100. We come back to this and try to evaluate this on the basis of first that assuming that the end fixity is 100%. That means it is fully rigid. That is the usual condition, and therefore, we should go with that, and then we will see that how the results have to be interpreted. So, what are the conditions? So, at x is equal to 0 here and x is equal to L here, we say y is equal to 0, it has to be 0, it is connected there, and also this relative slope is 0. Okay. So, if you apply these conditions, yeah, connection. Okay, this remains 90 degree, therefore, this does not deflect with respect to this.
So, there is no slope.
There is no slope.
Therefore, these welds are also being stressed. Welds are also being stressed. This particular
No, we are putting the bracket, and therefore, we are assuming that the welds are not getting strained. The entire structure is rotating. So, somewhere here the stresses are coming. So, now at this moment I am ignoring that. So, if I ignore that, then because of this particular pressure, my structure should deflect like this only. Okay. So, putting this boundary condition, we get the value C is equal to D is equal to 0 and A is equal to minus. I am straight away writing these values. And then we can write the shear force. Okay. Write the expression B. Moment and displacement y. I have forgotten to put EI here, EI will come here. Okay. So, after that EI comes down here, x to the power 5 120 plus hx to the power 4 24 minus 3L square by 20 plus HL by 2 this term, x cube by 6 L cube by 30 HL square by 2. Okay. So, these are the expressions you get after substituting and evaluation of these A, B, C, D and substitution. And if you try to plot the curves, what you will get here, this is your bending moment curve, and this is your shear force SF curve, and this is the datum line with which I have got the thing. So, now because I considered here the datum as 100% fixity, so we say that datum for 100% and fixity. Okay. Now, let us try to see what happens if the two ends were supposed to be simple support. If the two ends are simple support, then the bending moment should be 0 there. Okay. So, if the bending moment is 0, then if you join these two lines and start measuring the bending moment from this datum, then they are 0. Okay. So, we can say that this is the proposed datum for 0% fixity. This is an assumption, because we are trying to make the bending moment 0 there. Okay.
Please repeat that again.
See, according to these expressions, I have tried to plot shear force and bending moment, which goes like this. With respect to this particular datum, which is 100% fixity I have considered. Now, if I assume that the end fixities are 0%, that implies that the two ends are not capable of sustaining any bending moment. So, just making the two bending moments 0, if I join this straight line and consider this to be the datum, then with respect to this line I can say that this is for the 0 fixity bending moment curve. Okay. So, you have 100 here, you have 0 here, you have 0%, you have 100%. Now, as I told you that the brackets can be of different types, you can have the condition no bracket, this will mean 0% fixity. If you have moderate bracket, and you can have heavy bracket. When we say heavy bracket, we consider big dimensions, thick plate with a flange and so on and so forth, and in that case we can say it is 100% fixity. Okay. If there is no bracket, then we will say that it is 0%. It is just that the two plates are welded like this. Bulkhead comes to the,
Like two cantilevers.
no, you have the deck here and the bulkhead is coming and they are simply welded on the two sides. It will be still watertight. So, that connection I consider it to be no bracket. There is no bracket between the stiffener and the bulk in the underneath of the deck. Okay. So, that is 0%, and if there is a heavy bracket 100%, if it is a moderate, then I have to make a decision. Now, what is the size, what is the thickness, and so on and so forth. Of course, some analysis has been done, and if analysis is not there, people use their own judgment and try to put some 30% figure or 70% figure. Anyway, whatever may be the percentage, that only the experience will try to tell you. Now, with this condition, if I have to draw a bending moment diagram and the shear force diagram, what I do first, I use this expression, substitute the values, draw these curves, okay? And maybe that my bracket connections are such that I get in the top 30% and at the bottom I get 70% and fixity. So, this is my 0, this is my 100. If I say 30% in the top, so I try to measure 30% here. This is 0, this is 100, 70% at the bottom, this is 70%. And when I join these two points, this gives me the datum for the condition which I have chosen. And now, if I measure the bending moments like this, okay. So, this becomes the bending moment curve for this particular condition. Based on that, now you have to draw a parallel line with respect to this and find out where the maximum is coming. This is the value of the maximum bending moment, and this is the location where it is acting. Okay.
So this 50% and 70% fixed in one small difference.
See, depending on the bracket, say suppose I take a very small bracket on the top, obviously it is not 0% and fixity, because I consider if there is no bracket, then it is 0%. So, if I give a small bracket on the top, I have to, from my experience, I have to say that whether it is going to provide me 30% and fixity or not. So, let me assume that I have taken a small bracket and the contribution of that is to have a 30% and fixity. Similarly, at the bottom, I take a slightly larger size, a thicker plate, no flange. Okay. If I take a flanged one, then I say 100%, there is no flange, and therefore, I say that it is going to provide slightly more. So, it is 70%. So, this is 0, this is 100, proportionately I take 70% here. This is 0, this is 100, proportionately I take 30% here, and then I join these two points to get this line, and this is the datum for the bending moment and the shear force. Okay. So, with respect to this, now I try to find out where the maximum occurs, and how do I get it? I have to take a line parallel to this. Wherever it becomes tangential to this curve, that is the point where the value is maximum, and this is the position from top or bottom wherever you try to measure, that at this location the maximum stress is coming. It's okay. So, once I locate this, then at this level, whatever is the maximum bending moment, that bending moment I note, and then whatever is the permissible stress value given to me, based on that, because sigma is equal to m by z. So, I try to find out, because sigma is known to me. So, I try to find out the section modulus required is okay, and this is nothing but this value is I by y. And based on this, now I can design what this combination should have. because this is known to me, this is known to me, or I can find out what is this, and I should get what is this stiffener. Okay. So, this as a 2D I am trying to analyze it, sorry, as a single dimension. Now, what are the drawbacks here? I think I should stop now. Considering the flooded condition of the bulkhead, then the stresses generated due to the transverse load is much larger than whatever is imposed in due to the in plane stresses. Okay. So, if we try to isolate in plane with the out of plane, we find that it will be better to just make an analysis on the basis of out of plane method, and then we can also superimpose the stresses calculated on the basis of in plane forces. But yes, when we try to do a detailed analysis, at that time attempt is made to take all the forces simultaneously to get the true nature of the stresses in that particular structural element. Right. Now, here my primary member is between the second deck and the tank top, because the span is more and the load is of this nature. So, we set up, we are considering it as a beam. So, from here I set up some coordinate system and I say that my x is measured this way to some level here. Right. Now, if you take a cross section here for this particular strip, you will find that this is the plate width to which some stiffener is attached, usually a bulk plate, and at this level a constant pressure is acting here, which is of this intensity. Okay. I have just taken a cross section here and drawn here. Right. Now, this spacing as we have seen is S, and if we say that the water density here, or whatever you call it per unit area, then the pressure which is acting here or the loading onto this beam, right. Then let us take a section somewhere here. Draw the plate. This is the bulkhead plating, and then the hydrostatic loading in flooding condition will go right up to the top.
There is complete flooding.
When we say flooding condition, then we are saying that it is still floating, but wherever is the, whether it is up to the deck or up to some predefined line or whatever it is. Okay. So, this is loaded like this, right. Now, this is the load which we have seen, but if you see the construction, then usually what we will find that somewhere here you will have a double bottom here, a usual construction technique. Within the double bottom you will have certain girders here, and the bulkhead that, then getting the stress value is not a big problem, because section modulus is known to you, bending moment you are calculating, m by z will give you the stress level. Okay. Then many a times, if suppose you are having a 3 point supports, you have this, you have this, you have this, or as I told you that stringer is there. Okay. That's it. Say you have used a stringer here. So now you have one support, you have second support, you have third support. You have done this type of a beam problem with Professor Sheikh, I suppose. Yes or no? You have done it, multi-span problem or multiple support problem. Huh? Indeterminate beam problem. You have done it. So you can even start that way, because in all those methods which we have used, you can start applying it to any type of problem. You can say the bulkhead bending, you can even say that the top deck bending, you have the hatch end beams, you have one bulkhead here, another bulkhead here. So if I try to say this is the bulkhead, this is the deck, you have the bulkhead here,